All right, we're going to talk about hydrostatic filtration and blood colloid osmotic pressure. So this is a review from the cardiovascular system. So we talked about arteries. Arteries travel away from the heart, and they are going to narrow into arterioles. And in the arteriole, you have a sphincter, which is called the precapillary sphincter. This is literally a muscle that is within the arteriole. Now, your arteriole is going to be connected to your capillary bed, the site of gas exchange. So here's your capillary bed. And then your capillary bed is going to drain into your venule, which are tiny veins. And then those drain into veins and go to the heart. Now, again, this is a review. So, we have blood that is traveling from the heart. Now, one thing that we do need to review is your blood. Inside of your blood is going to have the plasma proteins. And your plasma proteins that are most important for hydrostatic pressure when reviewing this is albumin. Albumin is the plasma protein that is going to maintain the osmotic pressure inside of your blood vessels. So we have albumin. Remember, albumin is going to be a plasma protein. It is too large to exit the capillary bed, so it is going to stay within your blood vessels. So that is going to represent albumin, which is going to maintain the osmotic pressure. So we have our artery and our arteriole. The arteriole is a tiny artery. It's got the precapillary sphincter. And then you have your capillary bed, which is the site of gas exchange. And then you have your venule and your vein. So blood is moving in this direction. Now, when we say hydrostatic pressure, another word for hydrostatic pressure is going to be filtration. So your precapillary sphincter is going to constrict, which makes pressure rise up. So at the capillary bed, this is going to cause water and all kinds of other substances like gas, because the capillary bed's the site of gas exchange, to be forced out. So we do call this hydrostatic pressure, but it is also called filtration. Now we use that word filtration more in the kidneys, but it is still hydrostatic pressure. So you're pushing out water, you're pushing out gases, it's going to be electrolytes, it's all kinds of things that are being sent to the tissues. So we have gas exchange, so water is forced out by hydrostatic pressure, but because we force out water on the opposite side, on the venule, we need to attract water back in. So when we talk about albumin, water is attracted to albumin. That would be called blood colloid osmotic pressure. Albumin is what attracts it back in. So when you say blood, you're talking about the plasma protein. Colloid means it's a protein mixture. So the protein is albumin. Osmotic pressure. So the word colloid is referencing the proteins that are inside of the blood. Now, we can call this reabsorption. Now, it's important that you understand these concepts, because when we use the kidney and we're using the glomerulus, which is part of the renal corpuscle, we're going to have something called filtrate. That is going to be hydrostatic pressure forcing water out of the glomerulus so that you can create urine. But we have other pressures involved here. So we're going to talk about the pressures involved with the renal corpuscle, with the afferent and efferent arteriole. using the glomerulus, which is the capillary bed, but you also have the glomerular capsule. But this is just a review. So, when we talk about the glomerulus, we say that this is going to be glomerular filtration rate. So I'm going to make this a little bigger. So here's your afferent arterial, and there's your glomerulus, and then it's going to have the efferent arterial. It doesn't have to be perfect, but it's something like that. So we have to draw, and give yourself room, the glomerular capsule. So this is the renal corpuscle. So we're using the same words, hydrostatic pressure and blood colloid osmotic pressure, to discuss what's going on. So your afferent arterial is going to be to approach. So afferent arterial is bringing blood into the glomerulus. So it's a little bit different as far as the heart. And your efferent arterial is going to exit. But we still have to filter out the blood. The nephron, the renal corpuscle, is where all of this happens. So blood enters into the renal corpuscle, which is part of the nephron. So we could say this is the renal corpuscle. And it is part of the nephron. So how we create filtrate or urine is going to be right here. So what we say is the glomerular filtration rate. We want to know how much filtrate is being produced by the glomerulus. The glomerular filtration rate is going to determine how much urine you produced, and basically we have to control your GFR. Now, your GFR, when we talk about how much you actually filtrate, you're going to filtrate 125 milliliters of blood at a time per minute. So we're going to talk about what is going to go in and what's going to exit. But we also have to talk about albumin. Albumin is still a plasma protein that is inside of your blood. So albumin would still be in your afferent arterial as well as your efferent arterial because it's too large to exit. So we still have albumin. So we're using the same terms, hydrostatic pressure or filtration, and we're still using blood colloid osmotic pressure. Now this is going to determine the amount of glomerular filtration rate. So we have certain pressures that are going to create filtrate. So the pressures that create filtrate, the first thing is as it goes to the glomerulus, which is the capillary bed. So we could label this glomerulus. The glomerulus is the capillary bed. So when we talk about the capillary bed, the first thing that we always do is hydrostatic pressure or filtration. And we're talking about the glomerular filtration rate. So the first pressure that determines the amount of filtration is going to be hydrostatic pressure. So you are forcing water out. This is going to be filtration. So we say that hydrostatic pressure is also going to be filtration. So you have your hydrostatic pressure. That is literally filtration. So we're going to call this filtration. The substances that's pushed out is going to be water, electrolytes. Now, we also remember that we have albumin, which is too large to exit, so we also pull some of that back in. So we pull water back into the glomerulus so it can exit because you have albumin right here. So we would call this blood. Nope, not blood, because we're not in the blood. We would call this, well, I mean, technically it is blood, colloid, osmotic pressure. It's reabsorption. So this is going to make our glomerular filtration rate vary. So we force out water and we pull in water. This is called reabsorption. Now, when we talk about glomerular osmotic pressure, we need to know the pressure that is coming in. So this is going to pull in about 30 millimeters of mercury of pressure into the glomerulus so that it can exit. So we have to create urine or filtrate. So this number has to be a little higher or you would never produce urine. So we produce 55 milligrams of mercury of pressure, which is forcing water out. So ultimately, you're going to have more being forced out than pulled back in, which is going to end up being your filtrate or your urine. But there's one other pressure that is not inside of capillary beds that your glomerular or your renal corpuscle has. So your Bowman's capsule, which is here, is literally a wall. So what happens when you take a water hose and you spray water right at that wall? You would have pressure, so you would have water coming back to you. So when we talk about the renal corpuscle and the nephron and glomerular filtration rate, we have three different pressures. Your hydrostatic pressure, which is filtration, your blood colloid osmotic pressure, which is coming towards albumin, but you have one other pressure, and that's because you have this wall. So when the water from hydrostatic pressure hits the wall, you're going to force some of that fluid back into the glomerulus because it's spraying the capsule. So this is called capsular hydrostatic pressure. This is forcing it back in. So for each one of these, we could say hydrostatic pressure forces it out of the glomerulus. Blood colloid osmotic pressure forces it into the glomerulus. Well, capsular hydrostatic pressure, because the water is hitting the wall, it's forcing it back in to the glomerulus. So only a little bit of the pressure is going to actually force it back in. This is going to basically be 15 millimeters of mercury that forces it back in. I'm not really big on the numbers, but basically you're filtering the blood. Only 5 millimeters of mercury, I think, let's see, 30 plus 45, 10 millimeters of mercury are going to basically enter into the proximal convoluted tubule to produce urine. So when we talk about the glomerular filtration rate, it's not going to be that much blood per minute. But the nephron, the functional unit of the body, is filtering the blood, but we have different pressures which create our glomerular filtration rate. So to understand pressures that create filtrate, there's three pressures. You have your hydrostatic pressure that you need to understand. That forces it out. The next one is you have your capsular hydrostatic pressure, which is basically water being sprayed at a wall. It forces the water back in. So this would make it go in. Hydrostatic pressure forces it out. And the third one, because you have your albumin, you have your blood colloid osmotic pressure. blood colloid osmotic pressure is going to force it in. So before we can even go through the GFR, we need to understand pressures, and so this is a good review of that.